Welcome to the Plate Tectonics Lab. Today, we will be continuing the discussion of plate tectonics, including a brief description of Earth's composition, where the plates tie in, the mechanisms behind the different types of plate boundaries, and their prominent geological features. First, we'll start with some background information to provide you context for this week's lab. Earth is composed of distinct layers, each with unique properties and composition. The innermost layer is the inner core. It's made of solid iron and is approximately 1,270 kilometers in diameter. The inner core has extremely high temperature and pressure. Surrounding the inner core is the outer core, which is approximately 2,200 kilometers thick and composed of molten iron and nickel that moves in convective currents that help generate Earth's magnetic field. Surrounding the outer core is the lower mantle, which is 2,850 kilometers thick and composed of hot, plastic rock that moves in slow convection currents, which drives plate tectonics. Finally, the crust is the outermost layer of Earth. It is 5 to 70 kilometers thick and has two main types, oceanic and continental crust, which differ in identity and composition. Although the last slide shows the overall summary of Earth's layers, we can also look at Earth's chemistry and physical properties to gain a deeper understanding of our planet. From a chemical perspective, Earth can be divided into the core, mostly iron and nickel, the mantle, silicate rocks, and the crust, less dense rocks. From a physical or mechanical perspective, Earth can be divided into the inner core, solid, the outer core, molten, the mantle, viscous and partially molten, the asthenosphere, weak or plastic, and the lithosphere, which is brittle and rigid. Chemical layers are derived from Earth's formation and can be distinguished by distinct elements and minerals. Physical layers, on the other hand, occur due to convection currents and can be distinguished by temperature, pressure, viscosity, and plasticity. Boundaries between chemical layers are distinct, while the boundaries between physical layers are gradational. Understanding both views gives additional insights into Earth's composition and the forces shaping our planet. Chemical and physical models complement each other in geology. Something else you'll notice this figure is that the asthenosphere isn't uniform. This can be explained by the principle of isostasy. Isostasy refers to the way Earth balances and supports its weight. It acts like a buoyancy system, like how wood blocks float in water. Lighter continental crust floats higher above the mantle than dense oceanic crust. Mountains have deep roots below to compensate for high elevation. Like an iceberg floating, most of the mass is below the surface. Isostasy maintains equilibrium so that lighter parts of the lithosphere float at appropriate levels on the ductile mantle. Isostasy affects several key areas of interest in Earth science, including topography, landscape, responses to erosion and glaciation, gravity measurements, and plate tectonics. Understanding isostasy gives insights into Earth's structure, surface features, and responses to geologic processes over time. There are three main types of plate boundaries. Divergent boundaries occur where two plates are moving apart from each other. Convergent boundaries occur where two plates are colliding and moving towards each other. And transform boundaries occur where two plates are moving past each other. Plate motions at these three boundary types drive many geologic processes and features on Earth, from earthquakes to mountain building. Understanding plate boundaries helps explain the location of volcanoes, earthquakes, and more. A divergent boundary is where two plates are moving away from each other. In these situations, you can see mid-ocean ridges if you're looking at a divergent boundary in oceanic crust, or potentially a rift valley if you're looking at a divergent boundary in continental crust. Divergent boundaries are characterized by rift valleys, smaller earthquakes, continents separating, non-explosive lava flows. An example of a divergent boundary in the oceanic crust would be the Mid-Atlantic Ridge. An example of a divergent boundary in continental crust would be the East African Rift or the Red Sea. At convergent boundaries, plates are moving toward each other. In these situations, you can have three different types of tectonic settings. One, where you have two continental plates meeting each other. In this situation, both continental plates have roughly the same density, so neither one will sink beneath the other, and instead will create a mountain chain. Two, you can have an oceanic plate meeting a continental plate, where the oceanic plate is significantly denser than the continental plate, so the oceanic plate will subduct beneath the continental plate. This can cause volcanism at the margin of the continental plate. And then finally, you can have an oceanic plate colliding with another oceanic plate. In these situations, you can expect the older, more dense oceanic plate to subduct beneath the other oceanic plate. Some examples of convergent boundaries include the Andes Mountain Range, which is an oceanic continental convergent zone, the Himalayan Mountains, which is a continental convergent zone, or the Aleutian Islands, which is an oceanic convergent zone. Next, we have transform boundaries, which occur when two plates are moving past one another. At transform boundaries, you don't see any vertical displacement of rocks, just plates sliding past each other. You can often see zigzag patterns with divergent boundaries. Transform boundaries are characterized by no volcanism, major earthquakes, and a lateral offset of geographic features. An example of this is probably, the best example of this is probably the San Andreas Fault. Now let's shift our focus to geologic structures. Structural geology is the study of how rocks deform and the processes involved in that deformation. Deformation changes the shape, position, and volume of rocks in response to applied forces. These applied forces typically come from tectonic activity. The forces don't necessarily occur only at plate boundaries. The forces applied at plate boundaries can affect the center of plates as well. These can produce various geologic structures. There are two main types of deformation, brittle and ductile. Brittle deformation occurs when rocks fracture or fault under stress. Ductile deformation happens under high pressures and temperatures, causing rocks to bend or flow without breaking. The type of deformation depends on factors like rock composition, temperature, pressure, and strain rate. Strike is the compass bearing, or the line of direction or trend, of a line formed by the intersection of a horizontal plane, such as the surface of a lake. Such as the surface of a lake. Strike is usually expressed relative to north. Dip is the angle between a horizontal plane and an inclined or tilted surface, measured perpendicular to strike. The surface may be a contact between two rock layers, a fault, or a fracture. Earth scientists use strike and dip to notate 3D geologic features on 2D maps, like a piece of paper or a graphic for a presentation. This slide provides a more detailed look at strike and dip. The strike is where a surface intersects a horizontal plane, while the dip is the angle and direction of the steepest slope on that surface. Understanding these concepts is important for interpreting geologic maps and visualizing underground structures. Faults are rock fractures where two sides have been displaced relative to each other. Different types of faults result from different types of stress. Faults are important indicators of past tectonic activity and can help us understand the forces that have shaped an area's geology. A normal fault is caused by tensional forces pulling rocks apart. In a normal fault, the hanging wall, which is the block above the fault plane, slides down relative to the footwall, which is the block below the fault plane. This type of fault is common in areas where the crust is being stretched or thinned. Reverse faults are caused by compressional forces pushing rocks together. In this case, the hanging wall moves up relative to the footwall. A thrust fault is a special type of reverse fault that occurs at a very low angle, often less than 45 degrees. Reverse faults are common in areas of crustal shortening, such as at convergent plate boundaries. Strike-slip faults are caused by shear stress, resulting in horizontal motion along the fault plane. These faults don't involve vertical displacement, but instead cause a lateral offset of surface features. The San Andreas Fault in California is a famous example of a strike-slip fault. Folding occurs when rocks deform by bending instead of breaking. This ductile deformation can happen on various scales and under different conditions. Folds are often classified based on their shape and orientation, such as anticlines, which are upward arching folds and resemble a frown, and synclines, which are downward arching folds which resemble a smile. To better understand and interpret folding structures, geologists use three-dimensional block diagrams with strike and dip annotations. These diagrams help visualize the three-dimensional nature of folds and other geologic structures, which can be challenging to represent on flat maps. Here we see a syncline, or a smile, on the left side of the figure, and on the right side we see an anticline, or a frown. This slide shows an example of how three-dimensional block diagrams can be used to distinguish between different types of structures. The difference in dip direction between the left and right figures helps us discern a dome from a basin. A dome has layers dipping away from the center, while a basin has layers dipping towards the center. Next, we'll discuss information that you'll need to complete this lab. There are no safety concerns specific to this lab. When going through the lab, make sure you pay special attention to the units in the quiz questions in case you need to make conversions. Just in case you haven't had to calculate velocity in a while, remember that velocity is equal to distance divided by time. You'll need a computer or an iPad with the most recent desktop version of Google Earth. Unfortunately, the browser version of Google Earth will not work for this assignment. Although you will be provided with a worksheet and the maps that you will use in this lab, they will also be available for download on the instruction page in the module for this lab.